We good? All right, well, thank you, everybody. Glad you came. I'm Curtis Bragdon. I am account executive with Grammatech. That means, yes, I'm a sales rep. Don't worry, there will be no sales pitch in this room. For that, you have to go outside and talk to me. My own background actually is as a software engineer, so don't worry, I've got that credential. Most of the talk will be given by Joel Sherrill, whom you know from before, and we'll know again in another presentation after this, and then also Vince Hopson, who is field application engineer for Grammatech. So we're going to be talking about running CodeSonar static analysis on the RTEMS software. So RTEMS had been run through other static analysis tools in the past, and we talked with Joel starting last year about, gee, wouldn't it be nice to see whether or not CodeSonar can find something as well? And this is the results of that. So they'll go into details about that. That gives us, at Grammatech, a chance to see about how CodeSonar finds things in the real world. And for the audience, it shows you, here's what happens with a static analysis tool on some code that everybody cares about. One thing that's very important, there are other static analysis vendors in the market. There are actually other static analysis vendors in this room. There will be no discussion about the relative merits of one versus the other. Unless you want to come off to the table afterwards, then we can have a grand time talking about that. For now, it's just about, here's what happens when you run a code base through. Just real quick about Grammatech as a company. I see Gerard Holtzman in the audience. Gerard gave a talk yesterday. His group at JPL has used CodeSonar for a long time, including on the MSL code. So we're very happy about that. And has also been used, or CodeSonar has also been used on many other safety critical and economically critical code bases. As a company, we were founded 26 years ago. We've grown ever since then. We're a spinoff of Cornell, and our headquarters remains in Ithaca, New York. And we have a very large number of customers as well who are commercial and federal government. Okay, enough about Grammatech. Off to Joel.
Thanks. So you get to see me again. So no one noticed that my phone number was 867-5309 on the first slide. So so apparently it didn't get updated in one of the last revisions. So really this is just an experience report. So Craig and I have talked about this, and I guess we really started doing this about the first week of October. So we've really just piled through this very quickly, and so this is basically our experience. So the RTEMS code is highly stable. Some of the code goes back over 20 years. We've got source code history back to 95. Basically, one of the first things we found was, the question was, how do you even run the thing? And then how do you tune it to actually filter down the results so we find things that are useful? And one of the things we've learned from other tools is we give the benefit of the doubt. If a tool reports an issue, we will leave it open for months. I know the one real bug that's been found by any static analysis tool in RTEMS sat open for 6 months, and then one of us woke up in the middle of the night and knew how to reproduce the problem, and then it was fixed. So we don't just write them off as false positives. So that's a lesson I think you really want people to know. The other thing is and this is the ones I think that are interesting for the cases dealt here, they're code issues, but they're not, solving them is not necessarily obvious. The problem was actually more than just the code. So we're hoping to work out getting a copy of CodeSonar and keep this up as a regular part. So yeah, we have been scanned by something else. We're not going to mention names. We did it fairly regularly, but then the tool changed their submission process, and all of our scripts for doing it broke, and we didn't fix them. So I went back and fixed them again as part of this effort just to get a side-by-side comparison. No talking about that. We've traditionally focused, especially on coverage and static analysis and warnings. We start at the core with this and work out into support layers like file systems and networking and things like that. So again, we did the same thing in this part. We did look at issues on third-party code, but as a general rule, even when you find them, then we have to feed the problem upstream to find somebody else to analyze it, and it's usually code that's very trusted. Like we use the FreeBSD network stack, so it's usually not worth the trouble, and we focus on code that we own. We also have a shell with about 100 commands in it that are ported from BSD and some RTEMS specific commands. There were some flow issues that CodeSonar sees. They may or may not be real problems. I have no idea. They're too complicated to analyze in the time frame. So that's where we're going. We did resolve 10 to 20 issues of varying severity, mostly minor, and they are all, you can look into Git logs. So RTEMS is always compiled with a number of warnings. We're in the process of reducing the warnings reported and increasing the flags, so we're always doing this. We have a handful of native utilities, and the big thing we noticed here was actually they weren't compiled with warnings on, and no static analyzer we had ever run on RTEMS had paid any attention to them. So the worst problems were there, but nobody runs that code on a target, so that we weren't as concerned. Josh helped. So we did this on the head of the RTEMS build tree. While we were doing this, about 15,000 lines of code was added. The target was the Spark and the ERC32 simulator that's in GDB, so that's pretty familiar. That's how we configured it. We told CodeSonar to ignore a lot of third-party code, like MD5, the network stack, various things like that. And Josh and I triaged them. The ones that were obvious to fix, we fixed. The ones we needed help on, we sent out for community review. The important thing to note is our attitude is always that you should trust something being reported. And especially if you think you know better, because more often than not you don't. And it could, we've changed things over the years to just because the code was, if it was hard to analyze, then that meant it was hard to read. Because usually, so the analyzers can get confused, and usually just rewriting something makes it simpler. So one of the things we did, RTEMS is a fairly old code base, and we have, in the past some number of years, added a kernel assert. So our assert density has gone up enormously, and we added more with CodeSonar. And so we really don't care how long something's open as long as if we haven't adequately addressed it. So really the challenge is all of these is that a lot of this stuff is done by volunteers, and it just takes time. So first thing we had to do was same thing any project would have to do. We had to figure out how to build RTEMS with CodeSonar. Then we had to figure out what part of the source we wanted to focus on and what we were going to ignore. And then Vince really helped. He had a great approach for how to look at the results and actually do it in a productive manner, because I was getting wrapped around the axle on the JFFS2 file system. And how to interpret the results. Every tool reports results in a different way and uses a different set of language. And sometimes it's really easy to understand and sometimes it's not. And the other thing Vince helped with was how to look, which error classes tend to be real problems and are quick to identify, quick to fix, and we focused on those. One of the other things we did real quickly, we have places where we allocate resources at startup, and we knew from previous experience and design that they were not leaks, and CodeSonar found them as leaks. Well, they've been found that they're not leaks because, when you allocate standard in, out, and error, they're there for the whole life of the program. So that we just ignore the things like that. We knew to do it. The big thing that helped cut down on the first pass was teaching it the kernel assert, so it wouldn't keep analyzing a path that we had asserted against. There was a whole pass, thanks to Vince's pointing out which classes of warnings to tackle. There were some what I call obvious, but only obvious when they're pointed out. That code pattern there, I bet everybody in here who's written enough C has done it, and I don't know how it didn't notice another extra increment. Nothing had ever noticed the extra increment that's unnecessary on the last statement. Harmless, probably optimized away, but we got rid of it. There were other places where we added checks for return values. A couple of places where local variables were assigned twice without an intervening read. No idea how that happened. Probably editing, maintenance, cut and paste, who knows, but we fixed those. And then, interestingly, you'll find a variable set, and then you'll notice that there's a return 2 lines after it. Nobody ever looks at the variable, so that's pretty pointless, so we just deleted that. We also had some cases, because of paranoia, on the exit path, sometimes you would find a while one loop after you'd called exit, which seems stupid. So we added more asserts, and that's something that's just a style of programming that we've gotten better on. We just didn't do it in the early days because we thought it was confusing user and kernel asserts, and we didn't want them getting mixed up. And when we finally added a kernel assert, it made it. The native command line issue tools. These are things to convert like from binary to hex and S records and things like that. Basically, they're mostly old command line utilities that either somebody on the project has written, donated, or they came from somewhere else. And they had basically every kind of issue you can have: overrun, underrun, leaks, indexing issues. Basically, there's a large patch where all of these issues were fixed, and so that they've all been fixed. None of this code affects anything except doing file transformations on a development station. There's three really interesting ones, and then Vince is going to show you what the output in CodeSonar looks for these. We have in the past year, you might be surprised, we have a port of JFFS2. This is the stock off-the-net JFFS2 project code that's in Linux and BSD and everywhere, and they found about 30 issues with it. And we looked at them, and we realized it was just what we all probably in here would consider a very bad coding practice, where instead of doing conditional compilation to turn on and off logging and performance data, they use an if-def to turn a Boolean function to either return 1 or to return 0, and then there's a runtime check in an if is logging on. And then so the code, when it's 0, you get a dead branch, and when it's true, you get a positive. It's always true and unnecessary code. So it's just a strange code pattern. And I did find annotation in the code that they have ignored other issues in other static analyzers, so I don't really know. There is one piece of code left that has an issue raised in it, and it is in the RTEMS adapter file. And when I asked the guy who ported it, he said he copied the code from another OS port. So as Vince and I were talking, this actually is maybe if it's a real bug, which we didn't get resolution to decide if it was, it is in code that is marked with a file name that is OS specific and may have been copied over the years to any number of operating systems that use JFFS2. So this isn't just like a bug in a file that when it gets fixed, it's fixed. It's going to be broken in potentially every port of JFFS2. And it's a use after free or it's a double free. It's a double free. And we left it open because I still want to know, but it's some pretty ugly code. I wouldn't guarantee. Somebody wants to take a look at it, we'll help, and if you can figure it out and be confident in something, great, because it's not my code. There's another interesting one. This is in the interesting category. They flagged a couple of our portable chip drivers for having a divide by 0 in the baud rate computation. So if anybody remembers term IOs from POSIX, there's constants like B9600 to specify the baud rate's 9600. Well, it turns out that there is a constant for B0, which nobody remembers, and it's the POSIX code. When you set the baud rate to 0, you're supposed to hang up the modem control lines. So I looked at this code and I went, oh, divide by 0, put an assert in. That should never happen. And then a couple of days later, somebody told me to go reread the POSIX manual and make sure I remembered what I was doing. And so now I realize we're going to have to go through and review every UART driver that supports changing the baud rate to make sure if it supports doing modem control lines that it actually drops them when somebody does baud rate 0, or it returns not supported. So this is a case where, yeah, there was a divide by 0, but it's a real valid value because of the POSIX standard that actually ripples down into potentially every serial driver in RTEMS. So it's not going to be hard to resolve, but it's one that was way out of scope for a divide by 0. It was way off the chart. Probably would never happen in a real system. The other one is another that's kind of interesting is RTEMS shell. Someone on October 24th added a believe it or not, a GUI editor. It looks so you can just arrow around like Nano and run this edit files on file systems, and it works great. And it's got history back to 2002. So of course there have been many eyes on it, right? It's 15-year-old source. Well, it turned out that they found a buffer writing past the end of a buffer, and I again did what the obvious thing was. I tried to fix the code so it wouldn't write past the end of the buffer. I fixed it, committed it, and then the guy who ported it came back and went, that was debug code I never meant to leave in. And actually we noticed there's a comment today that says this is a really terrible hack, it shouldn't be left in the code. And you can look back in the history and see that apparently I didn't notice the comment in the top of the file that there was a hack to log the keys while he was debugging the key presses. So this is one where it was reported as a buffer overrun, but really what happened was you had to look into the history of the file. and the file had been committed with this code. Normally, when code is added to RTEMS, you add it as it originally came from the upstream project, and then you layer on the porting changes. So I thought the code came from the upstream project, and it actually didn't. So there was a minor hiccup in our source code procedures or habits, and that's why that one showed up. So this is the ironic thing is this just found code that had been in the tree a month, and it should have been deleted because it was debug code. So now here, I guess Vince gets to go up real quick.
Well, what I'm going to show you are the results that we found when we actually ran the software. This is the live system. You can't see anything yet. I'm getting there. So when you're looking at results from Grammatech, you're looking at a list of potential problems. There are warnings inside of the source code that we bring to light. The idea is that we want to make you aware of what's available to be found. So looking at the JFFS problem first, the double free, it's pretty easy to take a look at that right away. When you go into the warning itself, you're given a nice block of information about how it occurs. You can see here I've highlighted the root underbar I, which is the piece that will free twice. You can see events along the way. By going through this piece of recursive code, which is pretty icky actually, you can go and take a look at all of it. It's basically looking up and down a linked list, trying to be sure it's at the head of the list to do another deletion of some sort. And if you are, at some point, you'll come down here and free it. Notice it does do a recursive operation to go back up to a symbol up here, recurse. So looking at all that goodness, we can see now that a second free is probably not a good idea. Probably works most of the time. We're not certain it's a real problem, but we do have some indication that perhaps this should be reviewed, and maybe the information the code that's being used here should probably be looked at to see whether or not it's something that you really want to do. It also, one of the things that I've heard in my years of working with static analysis is simply that if it's so complex that it confuses an automated checker looking through the code, it's probably too complex for humans too. Maybe a refactoring thing would be something good here. The division by zero here is another warning that was found inside of the code. This is the one he spoke about second, where the baud rate is dropped to 0. In this case, you can go through with the baud rate divisor here, and you can see the baud requested is highlighted once again. If you follow through the path, now what CodeSonar is showing you here is the path through the code along with the warning. So we're telling you at the very top, we believe here there's a division by 0. With all static analysis, the thing you're looking at is as a friend had tapped you on the shoulder and said, I think you're doing something a little bit suspicious here. Maybe you need to step back and look at this code pragmatically. And that's really what static analysis is for. What we'll do is we'll show you where in the code the problem occurs. Secondary, the second thing we'll do is to sit back and give you information about the path it occurs on. So you don't have to guess, how did I get here? You can look and see exactly how you got here. By going through the code itself, all of the khaki colored lines are lines that were executed. Here you can see this if conditional. Which way did it go? By clicking any of the icons we have will tell you which direction the analysis took, so that there's no mystery about what's going on. Notice we went into a subroutine here, RTEMS, termios, bios to baud to number, which is the call right here. And it goes down through the source code and down. That's interesting. Anybody expecting a call? Down here you can see if we come through this piece of code, and if nap, in fact, is false, we're going to return a 0. Returning a 0 to that value that we saw from the call up here results in a division by 0 during the calculation in this area here. Is that obvious?
The simple explanation is that routine maps the baud rate constants like B19.2 into the actual number 19,2000, so you can do math on it. because it's just mapping the term.io's bitmap into the actual numeric value so you can do map on it. And since B0 is actually a valid value, it's going to return zero legitimately, which is the first thing we thought was the problem, that it might not be a legitimate value. But it turns out it's a special case value, and you're not supposed to reprogram the baud rate. You're supposed to drop like data DCD and
DTR,
those kind of signals, which also would indicate probably why no one's ever noticed it on RTEMS, because who uses a modem, right? I mean everybody's got 3-wire connections, so nobody
yeah, no one cares about modem control.
I'm expecting I'm going to add an if zero return not supported. It's what I'm expecting to return in a lot of places. But that's what's really going on. The code's more complicated than it actually looks. I mean, it's not very complicated.
And you can see here it's for Z8530. All right, so let's look at one last one. One of the things that you'll also get from static analysis, and this isn't really, I'm not really looking into for a bug here, but I wanted to show you a use after a, at the very top, it's a null test after a dereference. Now, one of the things static analysis does is it assumes the engineer knows what he's doing. So if the engineer knows what he's doing, then things along the path can be assumed to be true as you move through the code. If you find places where that's inconsistent, that's where you have a warning. And in this case, a null test after dereference simply indicates that target here has been dereferenced, yet down here is being checked for null. So no matter how you answer this question, target may have been known a priori to not be null. If that's the case, then why are you checking it for a null later on? If it can be a null, or you could approach this subroutine with a null, then it means that that first dereference is going to cause you a crash. So no matter how you answer that question, there's something to be done or something to be reviewed. And these are some of the things static analysis can bring to light for you. And we're almost out of time. Do we have any exiting comments?
I was going to say, the only thing to note is really, like, in this particular case, the design actually, we know that I think target is not null. So this is a case where this code predates us using defensive assertions. So this we'd put in a debug assert. But for the most part, these, if you notice, these are all like in file systems and device drivers. And that's kind of where you start to see what we've seen in RTEMS over the years is that the center point that everybody shares the code, it's had more eyes. And as you go out to the code that's on fewer and fewer targets, it's had less and less, it's had fewer and fewer eyes. And that's why you see problems like odd problems in device drivers or file systems. And the JFFS2 one is a pretty good example. That's really quite common code. And, but, I mean, you know, if anybody wants, if the IV&V people want to help us analyze these, we're more than happy to take the help because it's a fun game.
Any questions I can field for you before the next presenter? This.
I could be wrong, but this last one here looks kind of like a false positive because target just got reassigned right before that line. So it could have become null right there.
And if it had become null right there, see that this is one of the places that we're helping you by not forcing you to have to test fully, by going in and designing a test case that somehow makes a variable null. What we're doing is we're looking at this piece of code here, and if you're looking at this piece of code, if you forget about line number, I guess it's 79, and go from the if conditional only. So we're extracting the information from the path. And that's a very common assertion. We hear that all the time, especially for things like this where you have things like malloc or new, where you could potentially, malloc in particular, where you could get a null back as part of an allocation. Almost never happens. You don't see it that often unless you have more critical problems probably somewhere else. But what we're doing is we're extracting information from the path. So if at that line we're continuous, if we look at this line here and we say that this target is equal to a 1, we see that it's being dereferenced. That's all it's looking for. And at the second location, it's saying that target is being checked for null. So in this case, oh, I see.
Line 82.
Well, what is trying to what he's trying to say is, if you're checking for a null at 83, you should have probably checked for a null at line 80 also.
Precisely.
Oh, absolutely.
Absolutely.
He's not saying that 80, line 83.
Right, we're just saying that you're doing it backwards. Yeah, this, no matter how many times you've changed it in between these two, if you knew up here,
yeah, the second bullet says that. So either this check is redundant, or you need to add more checks.
Right.
Yeah, that
great,
makes
thank you
sense.
very much.
Yeah, and in that case, that's actually like the V node in BSD land, because the link node there is just the file system information. So you know that it should be there. I mean, it's a horrible bug if somehow you've gotten to the point of removing it and you actually don't have the file data at all in an open file descriptor. So if something's really wrong. So that one needs a defensive assert.
Any other questions?
Thank you. Thank you very much.
Thank you very much.